Well, welcome to our next journey together. And our next journey together in Organic Chemistry 2 is going to be this lecture module called Aromaticity and Reactions of Benzene. Now, aromaticity. That sounds kind of fancy. You know, classy people say aromaticity. So, what does that really mean? Well, to be honest, if you've had Chemistry 251 before, depending on who you've had, you could have ran across this concept of aromaticity before. But I'm going to assume that you haven't. If you've taken me for Chemistry 251, I did not really delve deep into the world of aromaticity at all because I knew that Chemistry 252 was going to focus on it very, very heavily. So now's our moment. Now's our moment to touch base with an aromatic compound and the reactions of benzene. But it's going to be more than this, folks. It's going to be more than reactions of benzenes and aromatic compounds, because we're going to talk about advanced reactions of benzene as well. What this means to you, I'm just going to be kind of blunt with you. We're going to be looking at this material for about a month, if not longer, depending on how the lecture modules shake out. So, benzene and reactions of benzene take up quite a bit of organic lecture material, and you have to get comfortable with these. If not, you're going to be a very miserable person for a very long amount of time in this class, and I don't want you to be miserable. You don't want to be miserable either. So, might as well get acquainted with benzene. You might as well accept to love benzene, because it's going to be around for quite some time. Now, let's go and take a look at this word that I've just introduced to you. And this word was an aromatic. So we have to define what an aromatic is, because there's a chance you have no clue. Well, if you just think about the word, what does it look like to you? I mean, I see the word aroma. Okay, so aroma means smell. So do these molecules have a smell? Yes, they do. Okay, well, do these aromatic molecules have bad smells? Absolutely, they do. I mean, everything from rancid butter to stinky feet to rotten fish. That's what aromatic compounds are for. Okay, well, what about good smells? There's good smells too. Do we have good smelling aromatics? And the answer is yes, we do. Aromatic compounds take up everything from, as I said before, stinky fit and rotten fish, all the way to the smell of bananas and pineapples and perfumes and colognes that you pay $60 and $70 for. Those are aromatic compounds as well. So this is kind of how the term aromatic was started. So they are smelly compounds, and they can smell good, and they can smell bad, but they do have an odor that's associated with them. However, this is science, folks. We just can't say the definition of aromatic is something that smells. I mean, that's great to begin to talk about it, but that really doesn't suit our purpose. There has to be more details, right? The devil's in the details, and the devil is getting ready to visit you in the next couple of lecture videos. So, aromatic compounds have a proper definition in organic chemistry. All right, and here's going to be the proper definition as it's stated in your text or reference literature. So I'm going to be all prim and proper for just a few moments, and you're going to see how boring this quickly can become if I was this way the entire time. All right, so the definition of an aromatic is, by memory, a cyclic and planar compound. That's not too bad. With an uninterrupted ring of p orbital bearing atoms containing an odd number of pairs of pi electrons. Folks, I'm old school, okay? I come from the days where teachers slapped your hands with rulers, and I'm not joking, all right? They did everything. They put us in corner time. They took our toys away. They smacked my hand because I'm left-handed, and then they also smacked my hand when I didn't memorize things that I was supposed to memorize for homework. Those were the good old days. Wish education was like that again now. So here's the definition of aromatic: a cyclic and planar compound with an uninterrupted ring of pi orbital bearing atoms containing an odd number of pairs of pi electrons. Okay, boring. What does that even mean? You're probably reading this and you're saying, what on earth are they trying to tell me? I mean, I know these are all the hot words. These are all the cushiony words that we use in organic, and it's all about using our words and our vocabulary. And this is great and all, but it doesn't really do us any good if we don't really know what this definition is trying to tell us. So we need to take a few moments here, and we need to flesh out this definition of an organic aromatic compound a little bit more. Now, one of the very first aromatics that you probably have been introduced to already is this structure called benzene. And we normally introduce this when we begin to talk about delocalization, and we also begin to introduce it when we talk about resonance forms. So benzene is a structure that's been around with us for a little bit. We haven't really focused on it that much. We haven't talked about it heavily, but oh, are we going to do that now? So benzene has a structure that you're seeing on your screen, a six-membered ring, and we have an alternating double, single, double cause you trouble bond. So double, single, double, single, double, single all the way around. It's very delocalized. This thing is very stable because of the delocalization that it has with it. This is not surprising. I mean, this is like Orgo 1 type of stuff. So nothing that I'm really telling you now at this moment in time is new. But benzene is classified as an aromatic compound, and that means that it fulfills this definition that we have just written out in all of these boring, crazy words of organic chemistry. So we need to kind of look at benzene first, and I think in doing so, it gives us a better idea of how to classify whether or not something is aromatic. Because if it is classified as aromatic, then this molecule is applicable to everything that we talk about in this lecture and the next. But benzene is kind of where we start because it's the simplest aromatic in a way that we use quite often. All right, so I'm going to go back and pull up an old school picture of benzene for you. And this is what 3 representations of benzene look like. I mean, now, granted, I know we've just drawn the structure of benzene. So we did this 6-membered ring, and we did double, single, double, single, double all the way around. We could also draw this as a 6-membered ring with a circle in the middle, because that gives us this idea that electrons can move throughout that molecule. They are delocalized. So they are the crazy kids on chocolate bars that go out and run in the subdivision up and down the streets. They'll eventually come back home, but they do have some leniency to get out and move and to go play and leave mommy and daddy at home alone with peace and quiet. All right, so this is the structure of benzene. So for A, what they're kind of showing you here are these figure 8 lobes. And if you had Orgo 1, or really if you've had general chemistry at this point, this shape should have already been introduced to you. And this is what we call the p orbital. So S's are spherical, P's are dumbbell shaped or figure 8 shaped. And they come to us in 3 forms. You can go a straight up and down figure 8, or you can turn this over to the side and you could do a left to right figure 8. Or because it's three-dimension, you can turn this kind of toward you and away from you, and that is another orientation of the p orbit. And this is what we call our px and our py and our pz orbits back in Orgo 1. All right, so this representation is focusing on the p orbital because if I go back to the definition, I see a lot of things that talk about p's, right? An uninterrupted ring of p orbital. Ding ding. Okay, so I know why they're showing me that structure now, because they're focusing on that p orbital of the structure and the molecule. And then it says containing the number of pi or pairs of pi electrons. Okay, so we'll get to that too, but pi electrons are typically located in p orbitals. Okay, so that's why we call them that. So for B, this is basically the concept that if you do have a structure like this, where a ring structure is in place, and each one of these atoms that are at the nodes, that's what we call that area with no purple, that's a node. At the node, that's where the carbon atoms are. If each one of these has a p orbital, then the issue that we see here is that these p orbitals take up space, and the p orbitals take up space and they just mush all together. All right? And they just kind of take up one big old kind of yard that all of these electrons just go play in. And the same thing happens on the bottom of the ring as well. So on the other side of that ring, you see all of these p orbitals that are pointed down. They all take up space. They're all basically shoving elbows into each other. And because of that, they all just mush as well. And you get this entire delocalized network, this big, big, big yard that all of these electrons just play in. And that's what the representation of B is trying to tell you. So yes, each carbon, each atom has a p orbital, but those p orbitals kind of mush together and they give us an entire yard for all of these electrons to play around until they're ready to come back home. And then C is the electrostatic potential map. And that electrostatic potential map basically gives you color codes, and those color codes are areas of green and red and blue. So green areas are very neutral. And if you take a look at benzene, the electrostatic potential map tells me that benzene pretty much is a neutral compound. If you look at the carbons all the way around, right, all of these are green areas all the way around there. So on the outside of this ring, does this mean that this molecule is neutral? Well, kind of it does. I mean, that's kind of what the electrostatic potential map tells me that's going on. And then here in the center of that molecule, I see an orange area. It's not necessarily red, so I'm going to say that this is just slightly negative. It's not full negative because that would be pure red areas that show up on these maps. Blue areas would be positive, and of course I don't see any blue at all, period, or any color close to blue that's on that structure for me. So this gives me an idea of how this benzene is basically structured. So I'm looking at a ring system, I'm looking at a delocalized system, and I'm also looking at a system that's neutral with a core, and that core is going to be slightly negative, and that negative is coming from the electrons that are associated in the ring system. All right, a couple of other things I want to tell you about benzene. So benzene's very toxic, and we use it in our laboratory. So we hope that when you do get your hands on a benzene substance or benzene itself, that you handle it with care. We don't want to breathe it in. We don't want to absorb it through our skin. We want to make sure that we really use the proper PPE for that. And benzene is all around us. What? Yeah, that's right. This toxic compound is all around us every day. So if you smoke cigarettes, that smoke is going to be filled with benzene. And benzene's very toxic, and benzene is known to cause cancer. Automobile service stations. Well, what? Yeah, if I take my car to the garage, and let's say I go into the garage and I want my oil changed, there's going to be various liquids that are organic based that any auto worker will use or any maintenance person will use. Those organic based solvents or organic based liquids have known benzene concentrations in them. So I've got to be careful with that as well. That's why we can't just dump this stuff down the sink and not worry about it. We have a proper disposal method for a lot of these fluids that go in and out of your car. Gasoline is another one. You got it. Every time I pull into a gas station and I put the nozzle into my gas tank and I pull the trigger, well, if you smell gas, then that means you're also smelling benzene as well. And benzene is a toxic, organic, aromatic compound. I smell gasoline. It's aromatic. There's aromatic pieces in it. Oh, okay. So anytime I expose myself to gasoline, folks, there's benzene, which is a toxic compound in it. It's actually so bad that we normally have to measure the levels of benzene in gasoline to ensure that it's low enough levels to be safely sold to the United States consumer. And sometimes the gasoline sources are going to be extremely high, and sometimes they're extremely low. We just don't know. That's the purpose of testing them. Automobile exhaust. All of the stuff that comes out of your car. Well, if gasoline is getting pumped into your car, it's going to come out your car in some form or fashion. So benzene can also be found in that exhaust as well. Industry emission. Well, what is that? Well, we have these big chemical companies, these big chemical manufacturers maybe. They're producing stuff. And maybe it's just not chemical producers. Maybe it's just a run-of-the-mill factory. There's a chance that they are producing waste, and that waste has benzene in it. And then glues and paints and furniture waxes. That's right, folks. You go to AC Moore, you go to Michael's, you go in Home Depot and Lowe's. You get these paint strippers, you get these glues, you get the, chalk paint, which is in right now. All of these different types of materials have benzene that's inside of the formulation. So, if you're using these products on a regular basis, you are exposing yourself potentially to levels of benzene, and over time, it could be bad for your health. All right, so some of the properties of benzene that come along with this. If you expose yourself to benzene at very high levels, you are going to see death. That's it. So this is a problem for us. I mean, we don't want workers in a laboratory to die, and we don't want you as a consumer to buy a product that has high levels of benzene in it, so that could cause death as well. But this is short-term exposure to very high levels. And if you are exposed to it, it's probably not going to be high levels. You're going to be exposed to it in low levels instead. So what are some of the symptoms of benzene poisoning as it's happening to you, maybe as you're working with this substance? Well, drowsiness and dizziness is going to be one. And you're probably thinking, drowsiness? I feel this way every time I watch one of your videos. Well, that's not benzene poisoning. That's something else. Next is rapid heart rate. So rapid heart rate, you experience that every time a test rolls around. Okay, well, that's due to something else. So benzene does relate to rapid heart rate as well. Headaches. Okay, well, you probably get headaches when you try to do the online assignments and try to watch all of these videos in one sitting, and you're going to give yourself a headache because of it. But benzene will also cause it as well. Tremors, confusion, vomiting, convulsions, all of these are symptoms of low-level exposure to benzene, which means that your body is trying to give you a sign. You need to listen to yourself sometimes. I mean, that's why we have these symptoms. So if you experience any of these while you work in a laboratory environment or while you're working with a benzene or benzene-related material outside of a lab environment for some other reason, These are kind of the big exclamation points that you need to take a look at. So what else about benzene is a problem? Well, benzene loves to mutate DNA. Okay, that's kind of how it works. DNA is actually made up of some aromatic compounds as well, and you're going to see these. And DNA, because it's aromatic and because of the shape of DNA, benzene can literally kind of slide right into that system, and it begins to break apart the double strands of the DNA molecule. Okay, so in other words, DNA is kind of like a ladder that is twisted, right? So here's the ladder representation of DNA, and these two strands are held together by all of the bonds that are in the center, and those are the steps of the ladder. Well, benzene can actually go in, and benzene can sneak in between those two strands and just rip them apart from each other. And when you get ripped DNA like this, you begin to have problems because that DNA has to glue itself back together. That DNA can replicate. And if benzene is in that system, this can cause problems in the gluing back of the strands or in the replications of the strands. So because of that, it is a mutagen because it could disrupt how it comes back together, and that by definition is a mutated DNA strand now, something that's different than what you didn't have before. 1920s was really the first case of cancer that was recorded for benzene. In the 1920s, they were working on something that they called parafilm, not parafilm, but it was something like saran wrap. They called it some kind of film. I forgot what it was off the top of my head. But 1920s, GE was manufacturing this material. So they had all of their workers exposed to benzene, and they were making this saran wrap material for people, and they really didn't understand the dangers of benzene, and it was used as an ingredient in that process. So before you knew it, whoa, excuse me. So before you knew it, these people were manufacturing the parafilm or the saran wrap film, and they were starting to get diagnosed with cancer. And some of them had been there for years, and they were up in their 50s and 60s, but some of those had just been recently hired, and they were still in their teens, or they were, 21 and 22. So they knew that an exposure symptom was going on, and they pinpointed it to benzene, and that's how all of this mess got started. 1979, the chemical industry finally said, okay, yeah, there's enough studies with benzene now. It does have cancer-inducing properties. You got us red-handed, so we're going to put a little bit tighter measure on benzene, so that way if you have an employees, they don't overexpose themselves. So we admit it. You got us. Yeah, we're guilty. And then in 2006, benzene was found in 4 soft drink brands. And the reason is not because the companies were trying to kill everybody, but these companies were producing a formulation that included benzoic acid and vitamin C. And these two components came together and they reacted together to produce benzene in the final product. And benzene happened because of the heat exposure with the transportation issues. So they were literally putting bottles of soft drinks or things like Crystal Light, folks, on the shelves of the grocery store. And you would go and get these bottles and you would pop open the top and you would guzzle them and not think anything about it. But the problem is that benzene was contained in these drinks that you were drinking, and this is a toxic, and this is a poison, and it's a DNA, and it's a mutagen. So this is a problem with the structure. So if you want to know more about the soft drink industry, because there were tons of them that did it, and it wasn't just soft drinks, there were things like Juicy Juice as well. I mean, things that you give to your kids, you're going to be able to find that link right here, or just do a Google search and do benzene in soft drinks, and you'll find articles and everything, especially from the FDA, that talks about the studies that were happening in 2006, where we were finding higher than normal benzene related and sometimes over the legal limit of benzene in these drinks and in these soft drinks, as well as juices. So if you want to know more about it, type the link in or do a Google search and you've got it. All right, so that's a little bit about benzene. Now, I want to go back to this aromatic definition because we need to flesh it out. I told you that we were going to do this, right? That's the purpose of taking a class, to understand this stuff better. All right, so let's talk about aromatics, and let's talk about the criteria of an aromatic maybe in more details. All right, so number one, if I go back and read that very boring definition, what I'm going to find out is that they're talking about a ring structure. So I'm going to have a ring in place. If it's not a ring, then that means it's not an aromatic. Point blank. As simple as that. I've got to have a ring. So straight chains? No, they can't be aromatic. That's an easy decision to make. All right, number two, every atom, and I'm going to put every in big, bold letters right there. Every atom in the ring has to have a p orbital. Okay, well, what does p orbital mean? Well, that goes back to Orgochemistry 1. 251. It goes back to that very first lecture that we began to talk about. What is a p orbital? Okay, well, I'm going to give you a simple definition here, and I'm going to say double bond. It's more than just a double bond, though. Okay, this is the most common p orbital that we see, but it's more than just the double bond. So I'm going to just take a minute or two, and I'm going to go back to Orgo 1, and I'm going to talk about something like carbon. Okay, so carbon has an electronic configuration of 1s2, 2s2, and 2p2. That's it right there. If I did the orbital filling diagram of this molecule, and I only focus on the second orbit, 2, I have a s orbit that has 2 electrons in it that go in opposite directions. And then the p's, they have 3 directions, right? And this is a px and a py and a pz. And px and py and pz are just kind of commonly termed because they go in 3 directions, up and down, left and right, toward and away from you, right? That figure 8 shape. Well, this carbon has an electron here, and it's got an electron there. There's 2 of them. That's why that 2 is right there, 2p2. So in the second orbital, there's 2 electrons in the p. All right, so there's the first one, there's the second one. They do not want to pair up unless they absolutely have to. Okay, so while I go through this, I got to keep in mind that carbon needs 4 bonds most of the time, right? Okay, well, this is unpaired, and this is unpaired, and this doesn't have anything in it. So it looks like on its face value, the electronic configuration is going to tell me that carbon only needs 2 bonds, not 4. So what goes on here? Well, back in Orgo 1, what you should have learned is that we can take one of these electrons and we can promote it. And we get it out of its paired up situation and we allow it to become single. And now all 4 of these electrons are single, and this includes a S, and it includes 3 of the P's because all 3 are involved, and a single bond with carbon is called a sp3 bond. I mean, that's how all of this really got started. All the way back, weeks and weeks and weeks and semesters ago. This is kind of where we started our lecture material. Well, if carbon has a double bond in there, well, now we don't really need 3 different atoms. We just need a stronger bond between 2 of the atoms, right? So we don't need all 3 of these p orbits. We just need 2 of them. So if we come in and say, hey, we just really need 3 atoms, and this is a S and a P2, there's my sp2, that's what that means, and this extra electron is going to be in a p orbit. So this is the extra bond that is going to allow these 2 atoms to come together a little bit tighter. So that's just a quick review of what we were talking about with sp3s and sp2s and sps and Organo 1. And if you didn't have that in Organic 1, I'm sorry, I really am. Go back and again ask for a refund. All right, so for number 3, the next thing that we have to think of is that these have to be flat. If this is a proper aromatic, the structure has to be perfectly flat, just like a sheet of paper. So again, think about these molecules. They are three-dimensional objects. They have a shape to them. They take up space. But these molecules have to be perfectly flat in order for aromaticity to take place. And then finally, number 4, they have to have an odd number of what we call double bonds. Now, double bonds is what I'm going to use, but I want you to keep in mind these are really pi electrons that we are referring to. So double bonds is what we see most of. I'm going to be referring to double bonds quite a bit, honestly. So I'll just go ahead and define it with double bonds in the definition. But I do need you to understand that it is really a pi electron set. So there's going to be some problems maybe in the future, in another lecture video, when we go and start counting these up, and we'll kind of elaborate that on number 4 at that time. All right, so before I go, I just kind of want to show you an example problem of this. So here's our first 4 criteria for an aromatic. It has to be a ring. There has to be a pi orbit or a p orbit in every atom, double bond kind of. They have to be flat, and they have to have an odd number of double bonds. All right, so here's an example problem, and it says, which of these are aromatic? Okay, we're going to quickly answer these. Let's look at A. All right, so for A, number 1, a ring. Yeah, ding, ding, it's a ring. Number 2, every atom must have a p orbital. Okay, in other words, a double bond, or something similar to a double bond, a set of electrons. So if I take a look at A, I have a double bond here, and I have a double bond here. So this one's got a double bond, that one's got a double bond, this one has a double bond, this one has a double bond, that one doesn't have a double bond. So because of that, A is not an aromatic molecule. Now let's take a look at B. All right, so B, number 1, ring. Okay, so it is a ring. Number 2, every atom must have a p orbital. All right, so here, yeah, that's got a double bond. This one's got a double bond. This one, it doesn't have a double bond. So because of that, we cross it out. Notice I didn't even mess with the positive. I didn't really have to, because I knew that there was a carbon there that didn't meet the definition. So if I was unsure of how to handle this charge, it was okay. I just ignored it because that other carbon definitely made my decision. Now, let's take a look at C. Number 1, is it a ring? Ding, ding. Yep. Number 2, every atom must have a double bond, or pi electrons. All right, so this one's got a double, that one's got a double, this one's got a double, that one's got a double. All of you getting a double. All right, so ding, ding, that works. Number 3, is it flat? Well, that's something I don't know. Number 4, odd number of double bonds. There's 2 double bonds here. There's not an odd number. So because of that, that is not aromatic either. So because 3 told me it had to be flat, well, I just ignored it because I knew that it violated the 4th component of an aromatic definition. Now let's take a look at D. All right, so D, is it a ring? Yes. Number 2, every atom must have a p orbit. All right, so that one's got a p, and this one's got a p, and that one's got a p, and this one's got a p, and that one's got a p, and you might have to p, but this one does not have a p. Because of that, that one's not aromatic either. Now let's take a look at E. All right, E, is it a ring? Ding, ding. Number 2, every atom must have a p orbit. So this one's got a p, and that one's got a p, and this one, there's no double bond. So because of that, that is not an aromatic. And finally, F, number 1, is it a ring? So that rules that one out to be aromatic as well. Folks, that's how we determine aromaticity. That is how we know if something is aromatic or not. We go through the 4 rules, and if it violates one of those 4 rules, it is not classified as an aromatic, and it should be as simple and quick as what I just did. And if you want to do the sound effects, I think it makes it a little bit funner. Is that a word? All right, so in the next video, we'll pick up from here, and we'll keep trucking on, and we'll talk about aromaticity a little bit more, and we'll find out what's to come in the upcoming lecture videos. So let's kind of sit back, enjoy the show, and see what this material is going to bring to the table for me to enjoy.